Turbulence on a plane can be nerve-wracking. The announcement bell rings, the pilot calmly mentions rough air, and the plane starts shaking. But don't worry, planes are designed to handle turbulence without the need for pilot intervention. Passenger planes have static stability, allowing them to quickly recover from being knocked off course for safer and easier flight. Fighter planes, designed for air-to-air combat, prioritize maneuverability over stability. And one of the factors that affects the plane's ease of movement is how stable it is, or in other words, how unstable it is and thus how ready it is to deviate from a straight and level flight with minimal force of comment saying that this was a good thing. The more unstable the aircraft is, the more maneuverable it is. Surely that is a hot take from people who have not studied stability and control of aircraft in depth. So let's see why this is a nonsensical approach to aircraft design. Let's think about this with a simple analogy. Here we have two situations: a ball placed on top of a hill and a ball placed in a valley. If we push the ball on top of the hill even a tiny bit, it will begin to accelerate down the hill and will not stop until we put energy in to slow it down. And we will need to put even more energy in to return it to the top of the hill. This is an unstable system. The opposite is true for the ball in the valley. Apply a force and the ball will roll uphill, and gravity will now provide a restoring force to bring it back. It may oscillate back and forth a few times before coming to a stop, but it will eventually return to its original position. This is a stable system. So how does this apply to planes? Planes have three rotational degrees of freedom: pitch, roll, and yaw. Let's first approach this problem with regards to pitch stability, which is where the X-29 was extremely unstable. Small general aviation planes like Cessnas are designed to be very stable and so return to level flight automatically after they are knocked up or down by a gust of wind. But how do they manage this? Pitch stability is determined by three primary factors: the location of the center of gravity, the location and design of the wing, and the location and design of the horizontal stabilizer. The center of gravity for our Cessna is located about here. This is the point which all lift will act around. It's like the fulcrum on a seesaw. Our wing is located slightly behind us, and thus the lift it generates is slightly aft of the center of gravity. This would force the plane to pitch downwards without a counteracting downwards force further back in the plane, which is exactly what the horizontal stabilizer provides: a downwards force. This force does not need to be the same magnitude as it has a greater control authority. As a result of its greater distance from the center of gravity, once again, just like a seesaw, this is how a plane maintains pitch stability without any outside influences. But what happens if turbulence knocks our plane off balance? If the forces remain the same, the plane would continue on in whatever orientation the ghost knocked it into. This is not what happens. Just like our ball in a valley example, we have restoring force to bring the plane back to its original position. This is a result of how our horizontal stabilizer's down first changes with the pitch of the plane. There are two primary factors that influence this. The first is downwash. When air passes over the wings, it is deflected downwards. This creates a downwash of air behind the wing. This downwash strikes the top of the horizontal stabilizer, and this produces a downward pressure. The magnitude of the downforce on the surface is dependent on downwash, and the magnitude of the downwash is dependent on the speed of the aircraft. The faster we go, the more air is deflected downwards. The slower we go, the less air is deflected. Luckily, our speed is also dependent on our pitch. If the plane pitches upwards, it will lose airspeed and the downforce on the horizontal stabilizer decreases as it was. The weight of the plane acting through the center of gravity, forward of the center of lift, now wants to move the nose down again. The opposite happens when we pitch the nose down here. We gain airspeed and the downwash on the horizontal stabilizer increases, causing the downforce to increase, forcing the plane to nose up again. This explanation is often provided as a complete explanation. But it falls apart when you consider a tail-configured plane where the horizontal stabilizer is lifted out of the downstream airflow of the wing. Here are other factors. It comes into play as a result of the angle of attack on the horizontal stabilizer. Here, the horizontal stabilizer has a negative angle of attack. This angle of attack changes as the plane pitches up or down. If we pitch it up, the angle of attack decreases and thus the downforce decreases, allowing the weight of the nose to pull it back down. If the plane pitches down, the angle of attack increases and increases the downforce, which forces the tail of the plane back down. This is an elegant solution to the problem which is thrown out the window for planes like the X-29. Here we have the forces acting upon the X-29. In the long chute in the plane, the center of gravity and the center of lift have shifted backwards as a result of the forward-swept design. And thus, in order to stabilize the plane, the converts need to produce lift ahead of the center of gravity. Imagine pitching a plane upwards. Without downwash to increase downforce on the stabilizer, the nose pitches up even more with a small energy input. While this is great for wild maneuvers, it's not ideal for level flight. The X-29's control computers had to constantly adjust for little disturbance up to 40 times a second, but that wasn't the main issue. The problem was the steepness of the hill. If we make it too steep, it takes excessive force to return to level flight. We need to balance maneuverability and energy efficiency to maintain a straight and level flight. Conclusion: planes are designed to be stable and recover from turbulence without pilot intervention. Stability is achieved through factors such as center of gravity, wing and stabilizer design, and downforce.